My oral compendium is on Stephen Arthur Cook, who is a famous computer scientist who is famous for his research in computational complexity as well as proof complexity within the computer science field. Stephen Arthur Cook was born December 14th, 1939, and is famous for his research in computational complexity. He is an American-Canadian computer scientist and mathematician who made significant contributions to the field of complexity theory and proof complexity. He received his bachelor's from the University of Michigan and went on to receive his master's and PhD from Harvard. After he was done with school, he moved to California to be a professor at UC Berkeley. After his application for a tenure position was rejected, he became a professor at University of Toronto. Stephen Arthur Cook's most notable contribution was the development of the concept of NP completeness and the proof of the existence of NP complete problems. But to understand these concepts fully, or why his contribution was so important, we need to understand what P versus NP is. So P problems, or polynomial problems, are problems that can be solved by the computer in polynomial time. So this means that as the size of the problem grows, the time that it takes to solve the problem grows relatively slowly. NP problems, or non-deterministic polynomial problems, are problems where potential solutions can be checked quickly. However, finding the solution itself might be really hard. In simple terms, Cook's theory asks if NP problems, problems that can be checked really quickly, can also be P problems, problems that can be solved quickly. Essentially, he is asking if NP equals P. And this is significant because if it is true, if P equals NP, there's a lot of hard problems across multiple fields like computer science, mathematics, and physics that can be solved a lot more efficiently than how we are solving them right now. But if it does not equal each other, if P does not equal NP, his theory suggests that there are fundamental problems that cannot be solved quickly by any computer. Cook's contribution was really important because it gave computer scientists a way to identify and classify hard problems. His work provided an outline for identifying and classifying computationally hard problems. The primary problem for this was his Boolean satisfiability problem, or the SAT problem, which is NP complete. And Cook showed that if anyone could solve it in polynomial time, then someone could solve all problems in NP efficiently using polynomial time. He also contributed to algorithm design and analysis with his theorems. So NP completeness results have a profound impact on designing algorithm and analysis. They helped researchers identify problems that are unlikely to have an efficient solution and have guided development of algorithms. It's also important in cryptography. So certain cryptographic protocols rely on a combination of factoring large numbers or symbols, and understanding the complexity of these problems is very important for ensuring security of cryptographic systems. Also, it's very important for theoretical foundations. So Cook's work laid the foundation for many areas of computer science, like complexity theory, computational complexity, and the theory of algorithms. Overall, Stephen Arthur Cook's impact on computer science shaped the way researchers think about computational problems. How does his contributions relate to computer architecture? There is a few different ways, one of them being algorithm design for architectures. And since NP completeness problems are problems that are very difficult to solve efficiently, architects must consider the complexities in designing the algorithms and how much space they take up. Also in hardware implementation, so certain algorithms or computational tasks may require specialized hardware to achieve the desired performance or the most efficient performance, especially when faced with NP complete problems where regular software like on laptops might not be the most practical approach. They also think about resource allocation. So his theorems with NP completeness influenced decisions regarding like resource allocation and management within computer systems. So computer architects must now consider the computational complexity when designing mechanisms for managing resources like processor time and memory. Also, security considerations to consider about his theory. If NP and P equal each other, then problems that were once really hard to solve, like cryptography and the protocols within there to make sure that passwords and keys that are generated are secure, can now be hacked and solved a lot quicker than once thought.